Hi, and welcome to Smart India Hackathon 2019 Designing Digital Solutions Training Program. I am Rajiv Kale, a technical trainer at Persistent University at Persistent Systems Limited. In this second module on machine learning part 2, I will take you through the remaining classification techniques like support vector machine, k nearest neighbor, and then we will move to unsupervised learning algorithms provided by scikit library. Later on, I will take you through some of the best practices followed by machine learning professionals, and then we will end the course. So, let us begin. So far we have seen how machine learning is divided into different categories like supervised learning, unsupervised learning. Under supervised learning, we have seen two further classes, one is regression, other one is classification. In case of regression, what we are looking at is continuous values, and in case of classification, we expect discrete number of classes in the target column. In case of linear regression, we have seen in scikit how to use linear regression algorithm, and we also saw one example notebook on the same. In case of supervised classification algorithms, we studied how logistic regression is formed using a sigmoid function under which we feed linear regression output. After that, we looked at another classifier called naive Bayes classifier, which is based on Bayes theorem. After that, we took a look at decision tree classifier, which works in the form of if and else kind of flowchart kind of a approach, and which has a tendency to overfit. And after that, we saw one variant based on decision tree classifier, that is called random forest. Now we will look at another famous and very popular classifier called support vector machine. Let us look at this data set you are very familiar with. On the x axis we have tumor size, on the y axis we have age, and there are some green points, green circles, and there are some red crosses. They represent harmless and harmful as the two classes. Now typically, if we use a logistic regression on this, all that it requires to do is draw a classification boundary or a straight line that divides this data into two parts. For example, if your classifier draws a boundary like this, is it not looking a good classifier? Yes, it does, simply because it is serving the purpose. As you see, on one side of the line there are all red crosses, on the other side of the line there are all green circles. So effectively this particular straight line or this particular model appears to be pretty good. How about this particular line? Even this line looks good, because it is serving the same purpose of classifying green versus red. However, support vector machine takes into account something different. It is a futuristic approach, or what it does, it tries to figure out where my next incoming test samples would be. It rejects both of these lines and attempts to draw a line something similar to this, which is called a large margin classifier. So what it attempts to do is maintains enough margin on both sides of your data points. So that is why it is also called a large margin classifier. As logistic regression is based on linear regression, support vector machine is a variant of logistic regression. So all the inner workings which are based on logistic regression with a small mathematical tweak will also have tuning parameters similar to linear regression. All the regularization techniques that we use for linear regression are also applicable to logistic regression and in turn to support vector machine. Now you would be thinking that this particular graph is showing the data points which are already having a large margin, but what about data points if they are already mixed? For example, let us take a case here. Now in this particular case, if I ask you a question whether a decision boundary on the left hand side is better, or the one shown on the right hand side is better? Typically, looking at this classification boundary, the popular answer would be the one on the left hand side is better, because as you see there is no misclassification. All the red points are on the bottom side of the line, all the green points on the upper side of the line, and you are not finding even a single point going into the wrong class in case of a left hand side graph. However, there is a graph on the right hand side which is showing a classification boundary which is a vertical line, and if you look at this particular line, you will see that one of the red points, that red circle, is getting misclassified into the green zone. So, there is one point getting misclassified. So, naturally a popular answer would be that the left hand side classifier is better than the right hand side. However, in reality, in practice, the right hand classifier is chosen by support vector machine. Although one point is getting misclassified, remember these are all training data points, and something getting misclassified from a training data points is not of much concern. What its concern is how correctly I would be able to classify when I will receive a test sample which is not yet seen. So, this is called a large margin classifier, and there is a tuning parameter called C. If you maintain a large value for C, then it is unregularized, and if you bring the value of C smaller and smaller, that means effectively you are making better and better regularization. So, this SVM will naturally select the right hand side boundary which will work better in the field. So, we will take a quick look at the Jupyter notebook, but before that let me ask you a question. Now, supposing if you want to classify this type of data points, as you can see here there are some red points and green points, and they are mixed in such a way that no matter how you draw a line on this, it like this for example, or a horizontal line like this, or any other kind of line, these two classes are inseparable. To simply put, this type of data is non-linearly separable. How to handle this kind of a thing in with SVM? So, now SVM has got another variant called kernel SVM. Have you heard of any transforms in your college days? So, if you know Fourier transform or Laplace transform for that matter, what does it do? The whole idea of using a transform is to convert a data, convert a problem which is difficult to solve in one particular domain take it into a different domain where it is easily solvable, and then solve the problem and bring it back to original domain. For example, if you have a signal which has a noise on it, what teacher used to say us? Use the transform, convert it from time domain to a frequency domain, design a filter, filter out the noise, and bring back the cleaned signal back into the original domain, isn't it? Same way we have learnt in the colleges how we use logarithmic transformation. So, when teacher used to ask us to multiply two big numbers, what we used to do? We used to take log. Once the log is taken, we get two small numbers which are easy to add. So, we add those two numbers and then take an anti-log to get the product of the two big numbers. So, these kinds of transforms are handy to take the data into a different domain, make it simpler, solve the problem and bring it back. Exactly same philosophy is going to be used by kernel SVM to solve this kind of a problem. So, let us look at it. This is the type of curve which we are looking for. How to draw this curve? Now, as you know, logistic regression is based on linear regression, and the limitation of logistic regression is it can draw only a straight line. Now, because support vector machine is also a variant of logistic regression, the same limitation applies to support vector machine as well. So, there also you can draw only a straight line. However, there is a variant to support vector machine, that is called kernel support vector machine, which is capable of drawing curves, or rather I would say take the problem into a different dimension, solve the problem and bring it back. For example, look at this diagram. So, on the left hand side top portion there are some data, the scatter plot, there is a some data points which are blue and red, and this is a two dimensional data x1 and x2. Naturally, if I ask you to draw a classifier boundary where we are restrained to draw only a straight line, that does not look to be possible at all, since the data is non-linear. However, I can define my own kernel or a transform such as phi, for example, which will convert my data from x1, x2, that is 2 dimensions, to something like z1, z2 and z3, which is the 3 dimensional data. Now, I need to define my own kernel here. That kernel I can define something like this. For example, I can say z1 is equal to x1, z2 is equal to x2, and z3 I can define as x1 square plus x2 square. If I define my kernel in this fashion, z1 equal to x1, z2 equal to x2 and z3 equal to x1 square plus x2 square, and then apply that kernel on my original data set. Once I apply that on the data set, what happens is all the red points go up, all the blue points remain down, and once they are taken into 3 dimensions, as you can notice here, it is very easy to cut that into two classes by using a simple straight line. Once that is done, I can bring back that converted data back to my original 2D data, which you are seeing on the right hand side bottom portion, where a nice non-linear circular boundary you can see, which classifies blue points against the red points. Fine, we can see this practically happening using Jupyter notebooks. So, let me quickly jump to Jupyter notebooks and we will see demonstration of usage of support vector machine. So, I am going to classification 2 folder and there is one notebook called support vector machine. Let me open that notebook. As usual, I am clearing off all the output that was generated when this notebook was previously run. We are learning support vector machine, so I am importing data sets, I am importing metrics and I am importing from sklearn.svm import svc, that is support vector classifier. Once I import it, I load the data set. This is the famous iris data set that you are now familiar with, and what I am going to do is I am going to define model equal to svm.svc kernel equal to linear c with a value of 1, and then I am going to say model.fit on dataset.data, which is an x part, and dataset.target is nothing but the y part. So, to a model.fit statement I am giving both input and output, and once I execute this, my model gets trained and now model is generated. I can use that model using model.predict method. For in this particular cell, you can say expected is equal to dataset.target, which is nothing but an actual value, predicted equal to model.predict on a data. I execute this and then I get a classification report and a confusion matrix, which I had shown you earlier how to interpret. So, in this case, if you look at the confusion matrix, support vector machine is able to classify Setosa 50 numbers as Setosa, nothing went to the wrong class. In case of Versicolor, it could classify 49 correctly, 1 into a wrong class, and in case of Virginica, all 50 were classified correctly as Virginica, nothing went into Setosa or Versicolor. So, this looks to be it has better managed the classification. Let us look at the tuning parameters. And if I draw a classification boundary, I can show you. So, in this particular case, I am using interactive widgets to control the kernel that I am using. If I say kernel equal to linear, then the only regularization parameter is C, and gamma has no effect on it. And if I play with C, all that you can see is it is changing the classifying boundary. However, one thing to notice is they are all straight lines. Now, that is the limitation. So, how do we use kernel SVM? So, all that I have to do is I will have to select RBF. This is radial basis function. These are scikit library built in kernels, and I can play with the values of C and gamma and see how the decision boundary changes. So, with more regularization you can see what effect it is having. So, suppose I choose not to regularize at all, then you will see if I keep a very high value of gamma and choose RBF, you will see that this is a sort of an overfitting diagram here. So, you can see that all the blue points and the decision boundary is very close to all the blue points. In fact, if you can notice, let it stabilize a bit, because I have made too fast a change on my slider bar. It will take a while before it stabilizes. It is picking up the new values. Now, see this, see I have selected a gamma of 31 and a C of 6, effectively having both gamma and C very large values, which means that I am not regularizing, and if I do not regularize, what happens is these are the kind of decision boundaries it is drawing, and as you can see, it has drawn an individual decision boundary on one of the points which is further away from the normal grouping. So, this exactly means what we call it as an overfitting situation. It is completely memorizing where my training data points are and trying to figure out how to draw decision boundary to have all those data points within it. So, if suppose a new data point comes somewhere here, for example, where my mouse pointer is, that data point naturally in this particular case will get misclassified because its real class belongs to this blue group. Now, if I change the regularization and make it more regularization, you will see what it does. So, give me a minute till it stabilizes. You will notice now, as you can see on the screen, it is having larger and larger area encompassing those data points, which is slightly better looking picture than before. So, this is how the new decision boundary will look with some more regularization. If you increase the regularization further, it will be even better. And this is how you should use regularization techniques to control overfitting problems for your data sets, and then before you release the model in the field, you must check that your model is not facing from overfitting issues. Now, the data point that we saw on the PPT, I have one more notebook to show you, which I will quickly run. I will not take you through all the cells, but what I wanted to show you is how a mixed up data which is non-linear can be separated out. So, I will run all the cells in one go. We will not go through the code, but I wanted to show you this picture. So, this tells me that I have selected kernel as RBF, I have selected values of C and gamma, and then by playing with values of C and gamma, I can control. So, this looks much better bifurcation between the red points and blue points. So, this is how we can separate out non-linear data. So, this is a demonstration of what we discussed in PPT. That is about on support vector machine. It is very popular algorithm. It is about what we call it as an expert algorithm. In fact, support vector machine has some more variants as well. So, there is a regressor also, then there is a one class classifier also. So, as we go along, we probably will encounter some more variants of support vector machine. Okay, going back to PPTs, I will take you through one more algorithm, and that is called k nearest neighbor classifier. So, let me ask you a question. Supposing you go home from your college or work, and then you find that at home you have a power outage. Once you notice power outage, what is your first reaction? What do you do? So, typical reaction for us is to ask your neighbors. You just look at from your window to the neighboring apartment or neighboring building and check out whether they also have power outage. In case you find that they are also having power outage, you rather relax, thinking that yes, everybody seems to have power outage and eventually the power will come back. However, if you find that your neighbors have power and you do not, then you sort of panic, is not it? So, in the same philosophy, the same human psychology is used by this classifier, nearest neighbor classifier. All that it does is it asks its neighbor, what is your class? The neighbor replies with whatever class it belongs to, and this particular data point assigns that same class to itself. For example, take a look at these data points. These are the data points given to you. This is under supervised learning. So, you have right answers. So, on x axis we have tumor size, on y axis we have age. So, basically we have two input features, x1 and x2. x1 is tumor size, x2 is age, and we have right answers given to us. On the last column we have whether a particular combination of input is harmless or harmful, and this is the plot of that data points. Now, with this set of data points, we feed these data points to our k nearest neighbor classifier, and what classifier does is it keeps record of all the data points, and what happens is when the next test data point comes in or a new data unseen data comes in, all that it does, it finds its distance from all the other points, finds out which is the nearest one, and whatever the class nearest one belongs to, it assigns it to itself. For example, let us say this is the new test point. Now, this test point appears at the position I have shown here. Which is the nearest point to it? It appears to be that this red x seems to be the nearest point to this in terms of distances. So, it asks that point, what is your class? It says I am harmless, and so the prediction for this particular blue circle here will be harmless. But what happens if this test point had come somewhere here? Then again, as you can naturally see, this belongs to harmful area. However, just because there is one data point which is close to it of class harmless, it ultimately turns out that the class of that test point also becomes harmless. So, the solution for this is, instead of asking for one neighbor, it is better to ask more than one neighbors, multiple neighbors, and typically odd number of neighbors. So, you can take majority, and then finally the class depends on, if suppose if you ask 3 neighbors, then it will ask this one and this one, and then 2 of them say harmful, effectively giving the class for the new unseen data as harmful. What are the different tuning parameters for this? Nothing much, except what kind of distance measurement you can do. So, that in the scikit library there are various ways to measure distances between two data points. They are called Euclidean distance, Manhattan distance, and Minkowski distance, with different formulas shown to you. So, like in case of say x1 y1 and x2 y2 in 2-dimensional data, you can calculate distance between the 2 points with y2 minus y1 bracket square plus x2 minus x1 bracket square, and then the whole thing under square root. Similarly, even if the data is of multiple dimensions, for example 3, 4, 5, 6 dimensions, still the same formula can be applied to calculate distance between two vectors. So, this in nutshell is k nearest neighbor classifier, which works pretty good, and in fact the results shown by k nearest neighbor classifier are also very close to any other classifier. Let us quickly take a look at Jupyter notebooks. I have one Jupyter notebook to show it to you, so that you understand how to define, how to call in scikit k nearest neighbor classifier. So, as usual, cell all output clear. This is how I import and define. From sklearn.neighbors import k nearest neighbor classifier. This is how I run it. I am importing data set, I am importing matrix, and importing k neighbor classifier. After that, I am importing data sets, which is an iris data set, Then I say model equal to k neighbor classifier into bracket I am giving tuning parameter, number of neighbors is equal to 7 and metric equal to Euclidean. Now, this 7 can be 3, 5, 7, 9 or anything of your choice. So, here I am asking 7 neighbors, then I am doing a fit which means machine learning. Actually, in case of k nearest neighbor classifier, when you do a fit, it has hardly any work to do except recording the data points where they are. Its real work starts when it receives the new data point as a test point, where it needs to find out who are its nearest neighbors. So, I say predicted equal to model dot predict, expected equal to target, and then as usual I can see what is its score and what is its confusion matrix. So, in this case 50 Setosa are classified correctly, 47 versicolors classified correctly, 3 went into Virginica, 49 Virginica classified correctly, 1 went into wrong class, and the score the model score returned as 0.97 or 97% kind of thing. So, that is about the k nearest neighbor classifier. So, we learned, so far what we learned? We learned k nearest neighbor classifier. In supervised learning we learned linear regression and classification, and in linear regression we looked some of the Jupyter notebooks, and under supervised classification we looked at various algorithms like logistic regression, then naive Bayes classifier, then decision trees, then we looked at random forest which is variant of decision tree classifier. After that we learned that support vector machine which has two variants, one is a linear SVM which can draw only straight lines but with bigger margin, and another variant called support vector machine kernel variant which is capable of bifurcating non-linear data. Now, the time has come to look at unsupervised learning. So, what are the characteristics of unsupervised learning? In case of supervised learning, we said that right answers are given and we have to produce more right ones. In case of unsupervised learning, one thing that is noticeable is we do not have a labeled column or we do not have a target column at all. All that we have is the input feature data. In unsupervised learning, we have three subsections. One is called clustering, another is called anomaly detection, and third one is called dimensionality reduction. We will see these one by one. Let us see what clustering is. Clustering simply means in English grouping. So, what clustering does is, now let us use the same data that we are very familiar with, tumor size and age, and this is the kind of data given to us. What is the difference between what we are seeing on the screen just now and what we have seen earlier? In the case of earlier plotting, we used to see red crosses and green circles, is not it? So, basically there were two classes, one belonged to harmless and other one belonged to harmful. So, when the data was given to us, the data provider has not only given us tumor size and age, but he had also provided us with additional column which is called a target column or a label data we call it, and that target column contained class labels, for example harmful and harmless, and in case of iris data set class label was Setosa, versicolor, Virginica. In case of whether Sachin will play tennis or not, the class column contained whether he plays or he does not play. But now look at the difference here. Here this is unsupervised learning, we are talking about unsupervised learning where right answers are not given to you. That means all the data points are shown as crosses and in the red color. So, there is no distinction between data points as far as the given data is concerned. Now, what machine learning algorithm is going to do for us is to classify this data into number of groups. How does it do it? By looking at the similarity between the 2 points based on its feature inputs. Now, the question will be how many groups it is expected to make. Now, that decision of how many groups somebody would like to make out of it has to be given by the user or the one person whose requirement is to make clustering. For example, in this particular case, our interest is to classify between whether it is harmful or harmless. So, we ask the clustering algorithm to separate it out into two classes. So, once this data is fed into algorithm, it will split into two groups. Now, all that algorithm will return to us is the data points that belong to group 1 and the data points that belong to group 2. Algorithm will not be taking any part in labeling the data, like in this case whether this boundary on the left hand side is harmful or the boundary on the right hand side is harmful is to be decided by the user who has asked for making such groups. So, it is the user's requirement how many groups to make. For example, I will give a live example here. Supposing I am owner of a startup company and I have 200 employees in my company and I wish to give say Diwali gift or a Christmas gift or a New Year gift to all my employees, and I have certain budget for this particular gift. One of the approaches could be decide on one particular gift. For example, I can decide to give say wristwatches to all the 200 employees. However, someone can think about some better approach, like not everybody would be would love to have a wristwatch, as he might already be having one or two or more wristwatches. Or if I decide to buy say a set of books and gift it to all employees, some of the employees may not like because they may not be interested in reading. So, typically what the owner of this company can decide is he can decide to make say certain number of groups, say 4 groups, and he can decide to have a choice of the 4 gifts, like one of the choice can be a set of books, the other choice can be a movie tickets, the third one can be a sports gear, and the fourth one could be something like garments. So, depending upon the liking of individuals, these he can make 4 groups, and then he can ask admin to buy 4 different kinds of gifts and then decide to give respective groups the respective gift. That will work better. But then who decided to make 4 groups is the owner's choice. Is it possible to make 200 groups? Yes, why not? But it is not practical solution. I can't have 200 groups for 200 people and asking, I can't run after everybody asking what do you want. So, the better approach could be say practically decide 3, 4 or 5 groups, decide on which gifts to be given to which of the groups, and then once the algorithm returns you the groups with the employee IDs, you can then see what is the similarity within that particular group, and then you can probably buy the right kind of gift which all the people would appreciate. So, how to split? Machine does. How many groups to split? User has to say, and how machine splits it? Based on the similarity between the input features. Now, which are the famous clustering algorithms available in scikit? So, let us see one of them, K-means clustering. This comes under unsupervised learning, and I will explain to you the theory behind it and how it works in brief. So, let us say these are the data points given to us, and we are supposed to make groups out of these data points. Now, let us say we want to make 2 groups. So, the way process runs is something like this. The algorithm is handed over this data, and we also tell algorithm that I want to make 2 groups. The first step that algorithm takes is it throws the 2 random seeds on this data. So, as you can see on the screen, there is a red cross and there is a blue cross. These are the 2 random seeds thrown on these data points. Why 2? Because we have asked algorithm to form 2 groups. How are they thrown? Randomly. Then this is the first step. In the second step, what algorithm does is, it goes to each and every green point and asks it a question. It asks each green point, are you close to red or are you close to blue? If you are close to red, turn red. If you are close to blue, turn blue. This is the question asked to each and every data point. Once that question is answered, the data points change their color in this fashion. So, all the points which were closer to red, red cross, they turn red. All the data points which were closer to blue point, they turn blue. After this step, the next step is, these randomly thrown seeds, they move to the mean of those all the red points, and the randomly thrown blue seed will move to the mean of the all the blue data points. So, now there is a step of moving the seeds themselves to the new mean. So, they move in this direction, this moves in this direction, and eventually they will be at the new position. Once that happens, all the data points are changed back in their color to its original color, that is green. This is the end of iteration 1. Once this iteration is over, the second iteration begins and exactly follows the same 4 steps one by one. For example, with this new position of seeds, each of the data points is asked, are you now close to red or are you close to blue? If you are close to red, turn red. If you are close to blue, turn blue, and this is how all the data points change their color. Once this color change happens, the time has come to move the seeds once again to the new mean. So, this moves in this direction, this moves in this direction, and eventually the means move to their new position and all the data points go to their original color. And same cycle repeats again and again and again and again, till what time? Till the time you stop number of iterations. So, you have 2 controls in hand, number of iterations. So, you can specify when you call the algorithm that run this algorithm for say 100 cycles and stop, or other alternative where when this particular iterations will stop is when means stop moving. So, eventually means are moving to their newer places, and then one stage at some time a stage will come when the means will stop moving, and then we can say that this algorithm has converged and there are no further movements and two groups are perfectly made. So, this is how the algorithm works. It goes on and on and on, and it continues, and finally it separates into 2 groups. So, now the groups have been made. Now, the question to you will be, how do we determine how good the clusters are? Think of it, how well the clusters are. In case of supervised classification algorithm, it was very easy to find out how our classification algorithm has performed, how our trained model is behaving. How did we do that? We did comparison between the real class of a data point and the predicted class of a data point, because we already had true answers. We have this was a supervised learning, and in classification we had a labeled column which told us whether this particular flower is whether it is a setosa, versicolor or virginica and that type of real answers were given to us. What we did during model training, we split the data between training and testing. We kept the test data away so that we can evaluate the model. We trained the model using training data and evaluated using test data. We compared the expected value, that is the real value, with the predicted value, and that is why we got that confusion matrix, you remember. So, 50 setosas were correctly classified as 50 and nothing went into different class. In case of other classes, there were some misclassifications, and that is how we found out how our model is performing. But in this particular case, this is an unsupervised clustering algorithm where we do not have right answers. So, what is the way to find out how well the clusters are? Okay, so one of the criteria is within cluster sum square error. So, as you can see within cluster sum square error. So, now that you have formed two groups, for example, these two groups, all that you have to do is find out the distance of all the points within the group from its mean, square it and sum it. Same thing you apply in the second group. So, if that sum of the squared distances is lowest, then it is a better and better clustering. Obviously, if you make more and more number of clusters, naturally your within cluster sum square error will start going down and down. For example, suppose if you have 150 data points, and as an extreme case, if I decide to make 150 clusters out of it, then naturally every point will be in its own cluster, and then within cluster sum square error will be 0. However, that is not the only objective. Objective of clustering is in user's mind. Nobody else knows why he want to make groups. Like an example I gave you about a startup owner who wanted to give 200 people some gift, and he decided to make 4 groups. So, that was his choice. So, within cluster sum square error is irrelevant here. The purpose of the user has to get served. However, in our Jupyter notebook and scikit library, there are certain mechanisms which will help us to find out whether clustering is good or bad. Apart from within cluster sum square error, there are certain graphs like right hand elbow method and Silhouette plot, which will help us do that. We will quickly take a look at Jupyter notebook, but before that let me finish with one more clustering algorithm, and that is called agglomerative clustering. So, this is one more approach. This is also called a bottom up approach, and how it works is in this fashion. Now, this is called a dendrogram. So, if you see here, there are data points A, B, C, D lying in the space, and on the bottom, on the left hand bottom side, I have drawn A, B, C, D, E, F, G up to L. What you have to do is basically find out which are the two closest points here. As you can see from the data point spread in the space, A and B appear to be the closest to each other than any other point. So, I can join these A and B in this fashion. The next is J and K. So, I can go and draw a line here and join J and K together. This is how it starts working, and eventually it will join the points in this fashion. And all that is in our hand now is to make a cut somewhere. So, on the left hand side you are seeing vertical arrow, that is a distance threshold, and on the right hand side you are seeing an arrow that is going down, which is called number of clusters. So, all that is now expected, all that is required to be done here is take a cut somewhere. Now, supposing if I cut something somewhere here like this red dotted line and now what you have to see is how many vertical lines are coming down from this red line. For example, this is one line, this is second, third, fourth and fifth. So, there are total 5 clusters. In this particular cluster, what are the points? A, B, C, D, E up to E. These are the points under this line. Now, point F is in a completely different cluster, and that is the only point there. This particular vertical line, if you see, there is a point G, and that also is in a separate cluster. Look at this line. Now, this entire stuff, entire points from H, I, J, K, M and N will come under one cluster, and this point L will come under another cluster. As you can see, point L, point F and point G are anyway further from each other, and they are belonging to a separate cluster. So, with this red line cut, I am getting 1, 2, 3, 4 and 5 clusters, and those clusters are defined by respective points coming down from that line. So, as I change the cut, if I go up, then naturally I will get less and less number of clusters. If I bring this red line down, making the distance threshold smaller and smaller, I will get large number of clusters. So, I have to play with distance threshold just to get as many clusters as I want. This is called bottom up approach. Alright, so let me switch on to Jupyter notebooks and show you how clustering works. So, let me go back to Jupyter notebooks. I am in the unsupervised learning, and I'll take you to basics of k-means clustering. So, let me open this notebook. As usual, I clear all output that was previously generated, and then I can run these cells one by one and explain to you what is happening here. So, the first cell is matplotlib inline, so that I will get the plot within the Jupyter notebook itself. It is importing it. In the next cell, I am creating 150 data samples. This is a synthetic data, so I am just defining the data set, and then I am plotting it to show you how data looks. So, as you can see here, there are 150 scatter points shown on this particular graph, and naturally by human eyes you can see that there are 3 distinct groups. However, in real life scenario you will not get such distinction between data points, but let us see how clustering algorithm works here and how he makes 3 clusters out of it. For example, I will import k-means. This is the name of the clustering algorithm. So, I am importing that. And let me say number of clusters to be 3, which is natural looking thing here. So, to start with, I am just making number of clusters 3, init equal to random, and I run this, and I run this, and I am just plotting it, and you will see the plot itself how it looks. So, as you can see the number of clusters, he has formed 3 clusters. You can see a blue color, you can see a green color, and you can see a yellow color as well, and you will see their centroids. So, these are the centroids of these 3 clusters, and obviously within cluster sum square error will be called distortion here. So, if I want to get within cluster sum square error, I can print distortion, which is called km dot inertia, and then in this case you can see number of within cluster sum square error or distortion is 72.48. Assume that I just make I choose to make 4 clusters out of this. So, if I make 4 clusters with the same data points, let me see what happens, and you can see here it had make 4 clusters. One is this blue, yellow, red and green with their respective centroids, and naturally when I find out the within cluster sum square error, I expect the distortion to go down, because when we make 4 clusters instead of 3, naturally the within cluster sum square error will be lower. So, it is now 62. So, if I say let us make 5 clusters and see what happens. So, if I make 5 clusters, then it made these 5 clusters. So, green, blue, red, black and yellow, and within cluster sum square error now 55. So, if I go on increasing to number of clusters to say 150, naturally this distortion will become 0, but that is not the objective here. Objective here is to make as many clusters as user wants. So, let me stick to 3 because that looks natural bifurcation and bring it out. Now, I wanted to show you elbow method to find out the optimal number of clusters. So, let me execute this. If you here I am selecting number of clusters, and I can see from this graph on the x axis we have number of clusters, on the y axis we have distortion or within cluster sum square error, and you can see a noticeable drop in the within cluster sum square error up to cluster number 3 or 4. So, you can probably say that we should stop making more and more clusters after say point number 4, that is number of clusters is equal to 4 appears to be optimal. If you still go on increasing the number of clusters, naturally distortion will fall. However, there will not be a significant fall here. So, main thing to note is that the domain knowledge is essential. The user who is asking to make cluster needs to decide how many cluster it wants to make. But supposing if you don't have domain knowledge and if you still want to make some number of clusters, you can take help of such plot. There is one more method called Silhouette plot. I will show you that graph as well, and in this particular graph you can see lobes here. So, if I make 3 clusters, you see these 3 lobes having very uniform width and length. If you get the Silhouette graph in this fashion, then probably your clustering is good. However, if I say make 4 clusters in this for this particular database, I will get this lobes in this fashion, which are not looking uniform. So, 2 of them are very thin and short, 2 of them are big and even the length is more. So, that is not a very good clustering. If I make 5 for example, that is even worse. So, this Silhouette plot can also help you determine if the quality of clustering is good or bad. Alright, so that is about clustering. Let us move on. I will go back to PPT and cover whatever remaining topics are in hand. So, this is how clustering is made. Now, let us look at one of the other techniques called principal component analysis. While we were going through the material on data science, Python for data science, we just touched upon one of the techniques during data pre-processing or feature engineering, that we said that we will cover it in detail during machine learning topics, and now the time has come to look at what is principal component analysis. This comes under unsupervised learning. So, this principal component analysis is typically used in many fields. It is not necessarily only to be applied in machine learning. So, principal component analysis is used for data compression in communication systems. It is used for feature extraction in computer vision, or for example image processing, and in case of machine learning it is used for dimensionality reduction. Now, I will give an example. Suppose we have data points like this. These are 2 dimensional data x1 and x2, and we have 1 lakh data points like this, and if I do not have enough memory to store these 1 lakh data points. Typically, to store one data point you will have to store its coordinates, that is x1 and y1, and to store one coordinate I will need 2 memory locations. So, to save 1 lakh data points I will be needing 2 lakh memory locations, isn't it? Now, supposing I do not have 2 lakh memory locations, I have to manage somehow in 1 lakh memory locations. What I will do? So, what technique they follow is, from this data plot you can see that data is aligned in a particular direction or in particular axis. So, this is the axis around which most of the data spread is there. So, what they do is they draw a line like this, and what they do is a 2D data, they make it horizontal, and what they do is they drop each of the points which are above or below the line onto the line. So, effectively the new data on the z axis looks like this. So, we have some data which is 2D data, now I am converting into a 1D data. So, for the initial 2D data I had coordinates x1 and y1. In the case of new representation I just have one coordinate, that is z1, z2, z3, and I just can manage with half the number of memory locations. But then how do I reconstruct the data back? So, what they do is they turn the z axis to have original slope and original y intercept, and then simply drop this line, and this is how I get the data back. Now, you would say, is this the same data as I had in the beginning? What I had in the beginning was this kind of a data, but what now I have got is a new representation which is not exactly same as before, however very close to it. So, basically this is a lossy technique. Some data is lost. What data is lost here? Basically it is losing the information, that is the height of the data points from the new axis, that is the information lost. And if you are okay to lose some information, the dimensions can be considerably reduced by using a technique called principal component analysis, and there is a scikit library routine to execute this. Now, if you look at this original data, you have x y coordinates. So, if you look at their values, you will say 10.1, 20.3, 15.6, 24.5, 18.8, 26.2 kind of thing. These are nothing but x and y coordinates. After conversion, I get two components, PC1 and PC2. These are the two new axes. The information is mostly spread across PC1. So, I have that information stored. So, the PC2 is a orthogonal axis to PC1 going through its mean. So, my PC1 new values will be 5.5, 15.3, minus 25.8 kind of thing, and on the PC2 I have very small numbers 0.3, 0.16, minus 0.24. This is nothing but the height of each data point from PC1. So, in case of my earlier representation, I can't chop off either x or y. If I chop either x or y to save memory, I will be losing lot of data. So, that is not on. So, what I can do in case of transfer data is I can chop off PC2 here. So, I can retain PC1 and I can just chop off PC2 because that anyway contains a very small information. This is how we convert 2D data into 1D data. So, after transformation, all that I am going to save is PC1, not PC2. If I have to save both PC1 and PC2, effectively it means storing like x and y. But because I have less memory, all that I have to do is transform x and y into PC1 and PC2 and chop off PC2. That is how I can save half the memory location. This is how 2D data can be converted into a 1D data. Now, let us take a case of what happens to a 3D data. If now we have a data in the 3 dimensions, what is the way out? The way we draw a line on a 2D data, here in this case we can draw a plane on a 3D data. So, let me draw a plane here, and what the next step is to drop all those points on the plane. So, all the points which are above the plane will be on the plane, which are on the bottom of the plane will get up to the plane, and eventually I will get a 2D data. So, effectively I can bring down 3 dimensions to 2 dimensions. Earlier we learnt how to bring down data from 2D to 1D, and here we are learning how to do it from 3D to 2D. So, if I can bring down from 3D to 2D, I can definitely bring it from 3D to 1D. And so, mathematically, if I am successful in bringing 3D data to 1D, I can bring n dimensional data to even a single dimension, and that is an amazing technique which we can quickly demonstrate using one notebook. So, let us see how principal component analysis works. So, I am taking you to principal component analysis under wait for a minute, I have to go to Python for data science. Learning PCA is the notebook. I am opening that notebook. In this particular notebook, I will clear off all the cells first so that we get right output. In this notebook, we shall show PCA in action, how you can plot data after PCA transformation, which is originally form is having 4 dimensions. PCA helps us to retain most of the information even if we reduce dimensions to 2. Later we show effect of standardization while we apply PCA. What we conclude is, whenever we apply PCA, it is important not to forget scaling input data using one of the data scaling methods such as min max scaler or standard scaler. So, whenever you apply PCA, do not forget to do data scaling. That is what is the conclusion of this notebook. I will just run it and show it to you. This is to be run on IRIS dataset. So, as you know, IRIS dataset has how many dimensions? 4 dimensions. I am showing you a plot. Why I am showing you a plot with Seaborn? Simply because I wanted to show you that I can plot only 2D data. For example, in this case plotting, I am using sepal length and sepal width. So, what I am doing is I am chopping off petal length and petal width in my in my plot. I am not using that data at all. So, this is how the plot looks. Isn't it showing, is it in looking completely mixed up? Now, what I will do is I will apply PCA. So, I have the original data which is 4 dimensions, which is defined here, x is equal to iris, all the 4 dimensions are here, and then I am using PCA and I am saying number of components is equal to 2, which means bring down the number of dimensions to 2 dimensions. So, my reduced x will be PCA dot fit transform x, I am feeding x to it and it will generate reduced x. I am just showing you what are the new values for PC1 and PC2, and then what I am going to do is I am going to plot PC1 and PC2 with legend, and that is how the plot looks. Now, do you think that this plot is substantially better than this plot? This is simply, here I am chopping 2 columns, and that is why this plot is looking like this. Here I am not chopping 2 columns, I am converting, I am transforming my original 4D data into 2 dimensional data, that is transforming 4D data to 2D data without losing much information, and that is why I could successfully plot PC1 and PC2. So, the new axes are PC1 and PC2. Now, what I will do is I will apply this PCA on standardized and non-standardized data and show you the difference quickly. Feature scaling, standardization, we have learned this, I am applying on, and then I am applying a PCA, and then if you can see here, this is the plot before, this is the plot before standardization after applying PCA. Here again you are seeing some mixing, but if I do standardization and then apply PCA, I get a beautiful bifurcation in this way. So, clearly you can see the picture, green, then this blue and other color, they have been bifurcated nicely. Here the only step, additional step that I took is before applying PCA, I made sure to apply standard scaler. Okay, let us go back and cover some other topics. Anomaly detection. Unsupervised learning also contains one area called anomaly detection. And what is anomaly, by the way? So, anomaly is something that is not normal. So, let's look at the Catch Me If You Can notebook, 284K good transactions and 492 fraud transactions. With such a data set, even if you predict all transactions at good transactions, it can give you 99% accuracy. So, I will open that notebook and show it to you. This is basically on a credit card fraud detection. Let me go there and I will go to unsupervised learning, Catch Me If You Can, here. Let me find out where it is. Okay, it would be Catch Me If You Can. This is the notebook I want to show you. So, I will open that notebook and show you what are the contents of this. Basically, it is interesting to see what kind of data it contains. I won't run this notebook, as running this notebook takes a little while, but there is already an output generated out of it. So, this is a credit card fraud detection system. The banks or the concerned credit card company has given its data, and what this particular data set contains is there are many columns here. So, 31 columns, and the last 2 columns is an amount column and a class column. Amount is basically a transaction amount, and the class column is either 0 or 1. 0 means good transaction and 1 means a fraud transaction. And if you notice in this case, the type of data that it has, if you look at it, you are getting a 99% accuracy straight away. And the reason for this is, if you go down and analyze the data, you will find that one particular class, that is a good class, that is a good transaction class, contains what 2,84,000 transactions, and if you consider other class, that is class number 1, which is a fraudulent transaction, it just contained 492 fraud transactions, and typically that will be the proportion. Most of the transactions that happen with credit card or banks are always good. So, in 3 lakh transactions, if some 500 are fraud transactions, bank will pay us lot of money if we can catch some of these 500. There is no point in declaring that all transactions are good. Even if you declare all transactions are good and valid in such a data set, then accuracy you may get 99%, because the fraudulent transactions are very small, but the whole idea is to catch how to catch as many transactions from this fraud as possible, and that can come out only if we convert this particular problem into unsupervised anomaly detection problem. So, let me explain to you what anomaly detection is. Convert such a problem into unsupervised learning anomaly detection problem. Fraud is to be considered as anomaly. During model training, what we do is we can simply drop fraudulent transactions from the input data. So, all the input data that we consider for our algorithm is all good transactions, and we drop the class column itself. This will generate data points that are closer to each other forming a group. Once model is ready, new data point is sent to it. It is checked if it falls within the boundary of this group. If it does not, it can be classified as a fraud. For example, look at this particular picture. If you look at this picture, these are all the data points of a good transactions, and all these data points is the only thing that is fed to the algorithm. It notes down these points and forms a model. Now, what it does is, if a new incoming data or a new incoming transaction on a credit card, if it falls within this group, then it classify it as a good one, or if it falls outside the group, it can classify as a fraud transaction. For example, this red point, this is an unseen transaction coming in. If it appears to be, or if it happens to be in the position it is shown, then it says that it is a good transaction. If it appears somewhere like this, then it will say it is a fraud transaction. And how it does that? Using something called Gaussian kernels. So, Gaussian kernels are nothing but a hat type of structure. So, the top view looks like a hat, and these red circles, on the top of the red circle you have 1, and as you go away from the on the center, you will go towards 0. And what you do is you place this hat on this particular data recording, and whatever falls under this hat, you can classify it as normal, and whatever falls outside the hat, you can classify it as anomaly. And the size of the hat you can adjust depending upon the application. If it is a financial transaction and if you are very strict, you can keep the diameter of the hat very small. This way you can convert your supervised classification problem into unsupervised anomaly detection problem, especially for the cases where the two classes are skewed. That means unbalanced classes, like in the case of credit card fault, we have 2,84,000 odd transactions as a good one and 492 bad transaction. That is a completely imbalanced data. On such cases we can use anomaly detection technique. Alright, so let us move on and see what we can do with the algorithm that is used for it is one class support vector machine. So, this another variant which is used for anomaly detection, and this particular, now in normal situations you may not always get points in a circular area. So, what you might get data points in this fashion, and what you need to do is draw a curvy boundary around it, and this can be managed through individual kernels which are placed above individual smaller areas, and whatever falls, whatever data points which does not fall in under any of the kernels, you can classify it as a fraud, else it can be normal. Okay, that is about unsupervised learning. Let us quickly now move on to machine learning best practices. Streamlining workflows with pipelines. So far we have seen that we do we select scaling, we select dimensionality reduction, and we then select algorithm, and we then pass the data from one to another. what scikit gives us a facility is to put everything into a pipeline. For example, as you can see here, within a pipeline we have scalar, that is you can use either min max scalar or standard scalar. Then the data is passed on to dimensionality reduction for something like PCA, and then we select an algorithm, and then the whole data is passed through the pipe. It goes in a pipe and comes out of a pipe. So, instead of saying model dot fit, what all we can do is say pipeline dot fit, and instead of model dot predict we can say pipeline dot predict. And when machine learning professionals share their models, they basically share their pipelines, and the pipeline contains various things like scaling, dimensionality reduction and learning algorithms. Another good practice that is followed is cross validation techniques. As we discussed earlier, we split the data between training and testing, 70% in test training and 30% in testing. But what happens is, typically people go on tuning their algorithm based on what accuracy they get on a test data. So, in this process what happens is, if they are not getting good test accuracy, they go on playing with model parameters, eventually consuming the entire test data set and overfitting on a test data. So, the better way is to further split training data set into two, that is one set is called training set, other one is called a validation set. On the validation set you go on fine tuning your algorithm as much as you want, and once the model is ready and fine tuned, finally you use the test data just for the purpose of finding the final accuracy. That is how you this method is called a holdout method. But again there is one more problem in this method that there is a scope to manipulate where to have your training set and where to have your test set, or rather which samples to keep in a test set, which samples to keep in a training data set. So, it can be deliberate or it can be even without any intent. However, there can be hard samples in the training data set and sometimes simple samples in a training data set, or vice versa, effectively giving a wrong picture about the model performance. So, the better way designed to handle this scenario is to use k-fold cross validation method. Here the training data set is split into 10 parts. In the first iteration, first 9 parts is used for training and the last fold is used for testing. In the second iteration, first 8 and the last one is used for training and the 9th is used for testing. So, in every iteration the part of the data that is marked blue will be used for testing and the rest of them is used for training, in which in this case as you can notice here, at least once every data point is going into a test data set, and all the data, all the points in the data set are at least going into a training once and in the test once. So, effectively nullifying the effect of how the data is distributed. And then finally, using cross validation techniques you can declare the performance your model in terms of accuracy as a mean accuracy plus minus some variance. This is how this is one of the best practices. Now, let us look at learning with ensembles is nothing but collaborating with each other. We have seen many of the classifiers such as logistic regression, naive Bayes, decision trees, support vector machine, k nearest neighbors and so on. Is there a way where we can take advantages of each one of them, bring them together and make a collective effort to generate the final prediction? Yes, it is quite possible, and people have done lot of experiments with this. For example, look at this diagram. This is called a majority mode classifier. So, in a training data set is fed to many classification models. So, C1, C2, C3, Cn, these are nothing but your logistic regression, naive Bayes, decision trees, support vector machine and so on and so forth, all of them fine tuned and cross validated, and they generate predictions on a new data. Say they generate P1, P2, P3, P4, Pm, and then a voting takes place. So, whatever is the majority weighting is the final prediction. So, what is the drawback of this? This is sort of a teamwork. So, sometimes teamwork benefits or sometimes teamwork may not benefit at all. Sometimes it might happen, in some cases it might happen that a particular good classifier like support vector machine was the only one predicting correctly. However, because the rest of the weaker classifiers, they predicted incorrectly, and you take the majority. So, ultimately you may end up misclassifying a particular data point. This can happen. So, no, it is not a guarantee that doing a teamwork will 100% give you benefit. It is not like that. So, what about how can we treat this? Can we give its weightage? So, if we say let us give weight 1, weight 2, weight 3 to different classifiers, how we determine the weights? One of the ways is to find their training accuracy and then give weightages. So, instead of giving one vote to every classifier, we can find out which classifier works better on a particular training data set and give it more weight. That is one way. However, since we are learning machine learning, isn't it better that if we outsource the whole job of giving weights to a classifier, that will work even wonders? And this is why stacking approach came into play. Training data is fed to classifier 1 and then to classifier 2, then to classifier n, and then the output generated of these classifiers and then further given to a classifier, which in turn gives the final output. So, one particular classifier classifying correctly, other classifier not predicting correctly, third one predicting correctly for a given real value, it itself is a machine learning. Using this machine learning, you can generate, and this way you can cascade to whatever levels you want. So, this is called the stack generalization. This technique is used. While the stack generalization is used, there is another technique called bagging. Here the training data is split into different parts, smaller parts. This is called sample data, and this is fed to classifier 1, and then all these classifiers. So, in this case I am sure you have seen this type of a model before. Let me remind you of random forest. In case of random forest, we had subdivided big data into smaller parts and fed it to decision tree classifier. The only difference here is we can use any other classifier as well, but the philosophy is same. You split the data and feed it to a classifier and then allow it to overfit on that particular data, and then finally a voting strategy is applied. This is called a bagging strategy. In case of bagging is used typically when you want to reduce variance while retaining the bias, retaining the low bias. I mean, bagging is not recommended on models that have high bias. Parallel execution is possible naturally because you are splitting the data and feeding it to different classifiers. So, we have seen boosting, that is stack generalization, and bagging. Now, let us see what is boosting. Boosting is typically applied to weak learners. For example, if you have a particular classifier or if you have a particular student in a class who is not doing well, a teacher encourages him to do, and what teacher typically says is, okay, try again, do not repeat the same mistake. The same philosophy is applied for in boosting, and what they do is, to a weak learner they say try again, but have more focus on the ones that have been misclassified last time, and this way it goes on classifying. It misclassifies different points every time, but collectively after 3 iterations you will see if all the 3 are combined together and redrawn, then it will classify correctly. So, it is more of a iterative process, and there are certain algorithms like XGBoost, AdaBoost for this particular methodology. It converts weak learners into strong learners, unlike bagging. Boosting is a sequential method. So, that is about all. We have covered a lot of things during this particular module. We have covered supervised learning. Under supervised learning, we covered regression and classification. We looked at various classification algorithms called logistic regression, naive Bayes, decision trees, random forest, support vector machine, linear support vector machine kernel, k nearest neighbors, and later on we moved on to unsupervised learning, where we discussed clustering, dimensionality reduction, and anomaly detection. And after that we covered some of best practices including cross validation techniques, and then we finished with some of the other ensemble techniques. Thank you for going through this machine learning part 2. I hope you enjoyed this module. To the 2 modules on machine learning, we looked at various algorithms provided by scikit library on linear regression, on supervised classification, on unsupervised learning, as well as best practices. I hope that the 2 modules on scikit library based demonstrations as well as Python for data science would get you going for your Smart India Hackathon challenge. All the best for Smart India Hackathon 2019. Thank you.